Definition of Turing machine. In this video, we are going to see about definition of Turing machine. A Turing machine is not just the next step beyond a push-down automaton. It is, according to the Churchturing thesis, a general model of computation potentially able to execute any algorithm. The basic definition as well as examples that illustrate the various modes of a Turing machine, accepting a language, computing a function, and carrying out other types of computations as well. Variants such as multitape Turing machines, Nondeterministic Turing machines are introduced, as well as universal Turing machines, which anticipate the modern stored program computer. We adopt the Turing machine as our way of formulating an algorithm, and a few of the discussions in the chapter begin to suggest ideas about the limits of computation. Computation Model. In this animated video, we are going to see about Computation Model. Both of the simple devices, finite automata and push-down automata, are models of computation. A machine of either type can receive an input string and execute an algorithm to obtain an answer, following a set of rules specific to the machine type. It is easy to find examples of languages that cannot be accepted because of these limitations. A finite automaton cannot accept simple pal is equal to xcx to the power of r, x belongs to a, b star. A device with only a stack can accept simple pal but not an, bn, cn is equal to a to the power n, b to the power n, c to the power n belongs to n, or l is equal to xcx, x belongs to ab star. It is not hard to see that a PDA-like machine with two stacks can accept an, bn, cn, and a finite automaton with a queue instead of a stack can accept L. Although in both cases it might seem that the machine is being devised specifically to handle one language, it turns out that both devices have substantially more computing power than either an FA or a PDA, and both are reasonable candidates for a model of general-purpose computation. The abstract model we will study instead was designed in the 1930s by the English mathematician Alan Turing and is referred to today as Turing machine. It was not obtained by adding data structure onto a finite automaton, and it predates the finite automaton and push-down automaton models. First, the only things written on the paper are symbols from some fixed finite alphabet. Second, each step taken by the computer depends only on the symbol he is currently examining and on his state of mind at the time. Third, although his state of mind may change as a result of his examining different symbols, only a finite number of distinct states of mind are possible. With these principles in mind, Turing isolated what he took to be the primitive steps that a human computer carries out during a computation. Examining an individual symbol on the paper, erasing a symbol or replacing it by another, transferring attention from one symbol to another nearby symbol. Concept of Church-Turing thesis. In this animated video, we are going to see about concept of Church-Turing thesis. To say that the Turing machine is a general model of computation means that any algorithmic procedure that can be carried out at all by a human computer or a team of humans or an electronic computer can be carried out by a TM. This statement was first formulated by Alonzo Church in the 1930s and is usually referred to as Church's thesis or the Church-Turing thesis. It is not a mathematically precise statement that can be proved because we do not have a precise definition of the term algorithmic procedure. By now, however, there is enough evidence for the thesis to have been generally accepted. Here is an informal summary of some of the evidence. The nature of the model makes it seem likely that all the steps are crucial to human computation can be carried out by a TM. Humans normally work with a two-dimensional sheet of paper, and a human computer may perhaps be able to transfer his attention to a location that is not immediately adjacent to the current one. But enhancements like these do not appear to change the types of computation that are possible. A TM tape could be organized so as to simulate two dimensions. One likely consequence would be that the TM would require more moves to do what a human could do in one. Various enhancements of the TM model have been suggested in order to make the operation more like that of a human computer, or more convenient or more efficient. In addition, various notational systems, that is, programming languages, grammars, and other formal mathematical systems have been suggested as ways of describing or formulating computations. Again, in every case, the model has been shown to be equivalent to the Turing machine. Since the introduction of the Turing machine, no one has suggested any type of computation that ought to be included in the category of algorithmic procedure and cannot be implemented on a TM. Turing machine and computing functions. In this video, we are going to see about Turing machine and computing functions. A computer program whose purpose is to produce an output string for every legal input string can be interpreted as computing a function from one set of strings to another. A Turing machine T with input alphabet summation that does the same thing computes a function whose domain D is a subset of summation star. A Turing machine computing a function. Let T is equal to Q summation gamma Q naught delta be a Turing machine, K a natural number, and F a partial function on summation star to the power of K with values in gamma star. We say that T computes F if for every x1, x2 up to xk and no other input, that is a k tuple of strings, is accepted by T. A partial function f summation star to the power k produce gamma star is Turing computable or simply computable if there is a TM that computes f. Ideally, as we have said, a TM should compute at most one function. This is still not quite the case, partly because of technicalities involving functions that have different code domains and are otherwise identical, but also because if T computes a partial function f on summation star to the power 2, then T can also be said to compute the partial function f1 on summation star, defined by the formula f1 of x is equal to f of x comma a. We can at least say that once we specify a natural number k and a set C subset of gamma star for the codomain, a TM can't compute more than one partial function of k variables having codomain C. We are free to talk about a TM computing a partial function whose domain and codomain are sets of numbers. Once we adopt a way to represent numbers by strings, for our purposes it will be sufficient to consider partial functions on n to the power k with values in n, and we will use unary notation to represent numbers. The natural number n is represented by the string 1 to the power n is equal to 11 up to 1. The official definition is essentially the same as, except that the input alphabet is 1. The initial configuration looks like Q naught del 1 to the power of n1, del 1 to the power of n2, del up to del 1 to the power of nk. And the final configuration that results from an input in the domain of the partial function f is HA del 1 to the power f into n1, n2 up to nk. Combine several TM into composite TM. In this video, we are going to see about combine several TM into composite TM. A Turing machine represents an algorithm. Just as a typical large algorithm can be described as a number of sub-algorithms working in combination, we can combine several Turing machines into a larger composite TM. In the simplest case, if T1 and T2 are TMs, we can consider the composition T1, T2, whose computation can be described approximately by saying first execute T1 and then execute T2. In order to make sense of this, we think of the three TMs T1, T2 and T1, T2 as sharing a common tape and tape head, and the tape contents and tape head position when T2 starts are assumed to be the same as when T1 stops. If T is equal to Q summation tape Q naught delta is the composite TM T1, T2, we can obtain the state set Q of no halting states of T by taking the union of the state sets of T1 and T2, except that the states of T2 are relabeled if necessary so that the two sets don't overlap. The initial state of T is the initial state of T1. The transitions of T include all those of T2 and all those of T1 that don't go to HA. A transition in T1 becomes in T, where Q2 is the initial state of T2. Multitape TM. In this video, we are going to see about Multitape TM. Algorithms in which several different kinds of data are involved can be particularly unwieldy to implement on a Turing machine because of the bookkeeping necessary to store and access the data. One feature that can simplify things is to have several different tapes with independent tape heads and to be able to move all the tape heads simultaneously in a single TM move. To simplify the discussion, we restrict ourselves to Turing machines with two tapes, and it is easy to see that the principles are the same if there are more than two. A two-tape TM can also be described by a 5-tuple T is equal to Q summation tape Q0 delta, where this time delta Q into tape union del the whole square produce Q union HA, HR into tape union del the whole square into R, L, S the whole square. A single move can change the state, the symbols in the current squares on both tapes, and the positions of the two tape heads. Let us describe a configuration of a two-tape TM by a 3-tuple Q, X1, A1, Y1, X2, A2, Y2. We will define the initial configuration corresponding to input string X as Q0, del X, del. Similarly, the output will appear on the first tape and the contents of the second tape at the end of the computation will be irrelevant. Theorem. For every two tape TM, T is equal to Q summation tape Q0 delta, that is the ordinary one tape TM. T1 is equal to Q1 summation tape 1 Q1 delta 1 with tape subset of tape 1 such that for every X belongs to summation star, T accepts X if and only if T1 accepts X, and T rejects X if and only if T1 rejects X. In particular, L of T is equal to L of T1. For every X belongs to summation star if for some strings Y, Z, U, V, epsilon, tape union, del to the power star and symbols A, B, epsilon, tape union, del. Then Q1 del X or minus star T1 YHAZ. Nondeterministic Turing machine. In this video, we are going to see about nondeterministic Turing machine. A nondeterministic Turing machine, that is NTM, T is defined the same way as an ordinary TM, except that for a state symbol pair, there might be more than one move. This means that if T is equal to Q comma summation, comma tape, comma q naught, comma delta, and q, comma a epsilon q into tape union del, then delta of qa is a finite subset, not an element of q union ha hr into tape union del into RLS. We can use the same notation for configuration of an NTM. If P is a no-halting state, Q is any state, A and B are tape symbols, and W, Y, Z are strings. Means that T has at least one move in the first configuration that leads to the second, and means that there is at least one sequence of 0 or more moves that takes T from the first to the second. It is still correct to say that a string X is accepted by T if for some strings W, Y epsilon into tape union del to the power of star. The idea of an NTM that produces output will be useful, particularly one that is a component in a larger machine. We will not consider the idea of computing a function using a non-deterministic Turing machine, however, because a TM that computes a function should produce no more than one output for a given input string. Let L be the subset of 1 star of all strings whose length is a composite number, that is, a non-prime bigger than 2. Since a prime is a natural number 2 or higher whose only positive divisors are itself and 1, an element of L is a string of the form 1n, where n is equal to p star q for some integers p and q, with p q greater than or equal to 2. There are several possible strategies we could use to test an input X is equal to 1n for membership in L. One approach is to try combinations p greater than or equal to 2 and q greater than or equal to 2 to see if any combination satisfies p star q is equal to n, that is, if 1 to the power p star q is equal to 1n. Non-determinism allows a Turing machine to guess rather than trying all possible combinations. This means guessing values of p and q, multiplying them and accepting if and only if p star q is equal to n. This sounds too simple to be correct, but it works. If n is non-prime, then there are p greater than or equal to 2 and q greater than or equal to 2 with p star q is equal to n, and there is a sequence of steps or NTM that would cause the numbers generated non-deterministically to be precisely p and q. In other words, there is a sequence of steps that would cause it to accept the input. The non-determinism will come from the component G2 shown in the figure, which does nothing but generate a string of 2 or more ones on the tape. The other components are the next blank and previous blank operations NB and PB introduced in a TM M that computes the multiplication function from n into n to n and the equal TM. The complete NTM is shown below. NB produce G2, produce NB, produce G2, produce PB, produce M, produce PB, produce equal, where NB next blank, G2 component, PB previous blank, M multiplication functions, equal compare two strings. We illustrate one way this NTM might end up accepting the input string 1 to the power 15. The other possible way is for G2 to generate 111 first and then 11111. Both these examples illustrate how non-determinism can make it easy to describe an algorithm for accepting a language. Concepts of universal Turing machine. In this video, we are going to see about concepts of universal Turing machine. The Turing machines we have studied so far have been special-purpose computers capable of executing a single algorithm. Just as a modern computer is a stored program computer which can execute any program stored in its memory, so a universal Turing machine, also anticipated by Alan Turing in a 1936 paper, can execute any algorithm provided it receives an input string that describes the algorithm and any data it is to process. Definition of universal Turing machines. A universal Turing machine is a Turing machine TU that works as follows. It is assumed to receive an input string of the form E of t, E of z, where t is an arbitrary TM, z is a string over the input alphabet of t, and E is an encoding function whose values are strings in 0, 1 star. The computation performed by TU on this input string satisfies these two properties. TU accepts a string E of t, E of z if and only if t accepts z. If t accepts z and produces output y, then TU produces output E of y. A simple encoding function E and then sketch one approach to constructing a universal Turing machine. The idea of an encoding function turns out to be useful in itself. Some applications not directly related to universal TMs. The crucial features of any encoding function E are these. First, it should be possible to decide algorithmically for an arbitrary string W belongs to 0, 1 star whether W is legitimate value of E, that is, the encoding of a TM or the encoding of a string. Second, a string W should represent at most one Turing machine or at most one string. Third, if W is of the form E of t or E of z, that should be an algorithm for decoding W to obtain the Turing machine T or the string Z that it represents. Recursively and enumerable languages. In this video, we are going to see about recursively and enumerable languages. Recursively enumerable languages are the ones that can be accepted by Turing machines, and we distinguish them from recursive languages, those that can be decided by Turing machines. Only if a language is recursive is there an algorithm guaranteed to determine whether an arbitrary string is an element. We examine two other ways of characterizing recursively enumerable languages, one in terms of algorithms to list the elements and one using unrestricted grammars. Chomsky hierarchy, which contains 4 classes of languages, each having a corresponding model of computation and a corresponding type of grammar. As a result, there must be some languages that are not recursively enumerable and others that are recursively enumerable but not recursive. Context-sensitive grammars and linear-bounded automata. In this video, we are going to see about context-sensitive grammars and linear-bounded automata. Definition of context-sensitive grammars. A context-sensitive grammar, that is CSG, is an unrestricted grammar in which no production is length decreasing. In other words, every production is of the form alpha produce beta, where modulus of beta greater than or equal to alpha. A language is a context-sensitive language, that is CSL, if it can be generated by a context-sensitive grammar. We will discuss these grammars and these languages briefly, and we will describe a type of abstract computing device that corresponds to CSLs in the same way that push-down automata correspond to CFLs and Turing machines to recursively enumerable languages. Context-sensitive languages that may make it easier to understand why the phrase context-sensitive is appropriate. Because a context-sensitive grammar cannot have productions. No language containing can be a CSL. Every context-free language is either a CSL or the union of and a CSL. It is appropriate to think of context-sensitive languages as a generalization of context-free languages, and many CSLs are not context-free. In fact, just about any familiar language is context-sensitive. In particular, programming languages are the non-context-free features of the C language can be handled by context-sensitive grammars. In any case, if we want to find a model of computation that corresponds exactly to CSLs, it will have to be potentially more powerful than a PDA. Definition of linear bounded automata. A linear bounded automaton, that is LBA, is a phi tuple M is equal to Q tape summation Q naught delta, that is identical to a non-deterministic Turing machine with the following exception. There are 2 extra tape symbols and assumed not to be elements of the tape alphabet tape. The initial configuration of M corresponding to input X is Q naught of X with the symbol in the leftmost square and the symbol in the first square to the right of x. During its computation, M is not permitted to replace either of these brackets or to move its step head to the left of the or to the right of the. This idea is the origin of the phrase linear bounded. An LBA can simulate the computation of a TM provided the portion of the tape used by the TM is bounded by some linear function of the input length. The four classes of languages that we have studied, regular, context-free, context-sensitive, and recursively enumerable, make up what is often referred to as the Chomsky hierarchy. Chomsky himself designated the four types as Type 3, Type 2, Type 1, and Type 0 in order from the most restrictive to the most general. Each level of the hierarchy, which is summarized in tables, can be characterized by a class of grammars and by a specific model of computation.